Welcome back, class. Today we are going to start in on chapter 11. So this first video is going to talk about something called VSEPR theory, right? That's valence shell electron pair repulsion theory. And we'll talk about how we combine this with Lewis theory in order to predict molecular shapes. Okay, so let's get started. So VSEPR theory is a simple model that we can use as an extension, if you were, think of it as an add-on, to Lewis theory that takes our Lewis structure from a simple two-dimensional image of a molecule to a three-dimensional image of a molecule. And we do this by assigning a molecular geometry. So the premise behind VSEPR is that it utilizes the electron environment around the central atom in our Lewis structure and bases the idea that electrons want to get as far apart from each other as possible. So we think about the surrounding of the central atom in terms of electron groups. And an electron group can be one of essentially four things, right? We can have a single bond, we can have a double bond, we can have a triple bond, we can have a lone pair. But they all count as an electron group. And these groups of electrons want to get as far away from each other around the central atom as possible. And so by looking at the electron environment around our central atom, we can then predict the three-dimensional geometry. So, again, if we think back to our Lewis structure, we rely heavily on valence electron pairs, right? And we place these around our central atom either as bonds or as lone pair. And to emphasize what we said in the last slide, right? Each pair of electrons, whether it's a lone pair, counts as an electron group. Each bond counts as an electron group. It doesn't matter whether that bond is a single bond, a double bond, or a triple bond, because those bonds, whether they be 2, 4, or 6 electrons, occupy one area of space around the central atom. So if we take, for example, NO2, we look around our central atom, we see that there are 3 electron groups. We have a lone pair, we have a single bond, and we have a double bond. And the fact that we have 3 lone pair or 3 electron groups around it will help direct us toward the type of geometry that we're going to have. So when we get into the geometries, there are 5 basic geometries. Now, these are going to stem from the number of electron groups around the central atom. Now, we're looking at geometry where we can have a maximum of 6 electron groups. And that's going to encompass, 99.9% of the molecules out there, right? Very rarely do we see anything beyond 6 groups. And you won't see anything in our studies here. And each of the 5 basic arrangements comes from having a different number of electron groups. Now, in this particular book, they call these 5 basic arrangements electron group geometries. And it's sort of a stepping stone to get to what we're actually looking at, which is the molecular geometry, or molecular shape of the molecule. Now, if we have only bonds in our electron groups, then we will have one of these 5 basic arrangements, and that will become our molecular shape. Now, if we have lone pairs, then we have additional molecular geometries that can come from these electron geometries. And we're going to walk our way step by step through each of the 5 basic arrangements and all of the molecular geometries that can come from that. Now, we'll make a point here. We talked a lot in Chapter 10 about resonance, right? And the idea that some structures have resonant structures. So they have more than one possible Lewis structure with different electron arrangements. Now, we don't have to worry about resonance when we think about VSEPR because all resonance structures will have the same molecular geometry because they have the same electron environment around the central atom. They may be switched where the double bond is and stuff, but the overall environment is going to be the same. Okay, so let's start walking our way through the 5 arrangements. So we'll start out with 2 electron groups, right? So you have to have at least 2 electron groups to have a molecular geometry, right? If you have, anything less than that, you just have 2 atoms and it's always the same. It's a linear. So if you have 2 electron groups around the central atom, they will occupy positions 180 degrees from each other. So they will be, in other words, opposite sides, as far apart as they can get from each other. And we call that geometry linear geometry. So we could have a couple of different ideas. We have an example here with beryllium, which has a reduced octet, just like we saw with group 3 commonly, right? It had a reduced octet with only 6. There's beryllium compounds out there that we really don't get into too much in this class that can have only 4, right? More commonly, we see a linear geometry when a central atom makes 2 double bonds, or maybe a triple bond and a single bond, and so there only has 2 electron groups, and those groups arrange themselves again 180 degrees apart from each other, like CO2. Okay? So that's pretty simple. 2 electron groups, linear, 180 degree bond angle. Well, let's go to 3 electron groups. So with 3 electron groups, of course, those are going to arrange themselves as far apart as they can get around a 3-dimensional sphere. It turns out that the furthest 3 things that can get from each other is a planar triangle. And so we call this trigonal planar geometry. Now, as you think about a triangle, notice that the angles here are going to be 120 degrees in an idealized triangle. And so that's the bond angle we associate with trigonal planar geometry. Now, in reality, these bond angles could be slightly different depending on what the electron groups are. So if we have something like boron trifluoride, which has a reduced octet, so it has just 3 single bonds around it, then we have the idealized angle. But if we get sort of a more common structure where we have, say, 2 single bonds and a double bond, like we have in CH2O, right? Then you notice the angles are not the ideal angles. We have larger angles here, smaller angle here. Now the reason for that is the electron pair repulsion, right? So while a double bond and a single bond only represent 1 electron group, they do function differently a little bit in terms of the repulsion. So since a double bond is 4 electrons, it's going to repel more, right? So it's going to push these hydrogen atoms further away than if this were just a single bond. And so we get bigger angles up top, squished smaller angle down here between the 2 hydrogens. But generally speaking, angles are right around 120 degrees. Now, let's go on to four electron groups. So 4 electron groups, right, around a central atom, they occupy the corners of what's called a tetrahedron. So tetrahedron, right, is a geometric shape with 4 corners. Right? And when you have 4 things equally arranged around a central atom, they are going to occupy the corners of a tetrahedron, right? So you can think of this as sort of the balloon structure, right, where the central atom is there in the middle. You could think about this sort of geometric structure where the central atom would be located in the middle of this, right? And we can think about the four corners here being our things that are bonded. And this is what a tetrahedron looks like in 3 dimensions, right? And when you space 4 things around a sphere, the angles come out to be 109.5 degrees. And so the idealized tetrahedral angle is going to be 109.5 degrees, which is what we see in something like CH4. So 4 electron groups, 4 bonds, tetrahedral geometry. So the next 2 structures, 5 and 6, we get into molecules that have expanded octets. Right? So remember, to get to 5 electron groups, we're going to have to expand, right? To have 5, 10 electrons. And 6 electron groups is going to be 12. So these are only going to occur when we have expanded octets. Now, if you take 5 things and you space it around a central atom, you get something that is referred to as a trigonal bipyramid. And so you can envision it like this with balloons, where you have a central trigonal plane and one at the top, one at the bottom. So it's like you have 2 triangles with their bases connected. Right? So a trigonal, so it's a triangle base, bipyramid, pyramid above, pyramid below geometry. Now, trigonal bipyramidal is sort of a unique structure in the fact that it has 2 different bonding environments. It has what we call the axial bonding environment, which is represented by the 3 atoms in the trigonal plane in the center, right? And those are separated from each other by 120 degrees, just like in trigonal planar geometry. And then we have what are called the equatorial positions that are above and below that trigonal plane. And those are both 90 degrees from the atoms in our trigonal plane. So we have 2 distinct types of bond angles here. We have 120 degree angles within our trigonal plane and 90s between the equatorial and our trigonal plane. So that's kind of a unique structure because it has 2 unique bonding positions, right? We have axial and equatorial. And finally, 6 electron groups. 6 electron groups around the central atom will occupy the corners of what we call an octahedral, right? Which is a geometric shape that has 6 points, and it's called an octahedral, of course, because it has 8 sides, right? It's like having a square-based pyramid stacked at the base, right? So you have 4 atoms in the square plane part, and then 1 above, 1 below. Okay. Now, in this case, all of the bonds are the same, all 90 degrees, right? 90 degrees within our square plane and 90 degrees above and below. So we don't define different bonding environments because the angles are the same. So if you can rotate this, you can make any of these the equatorial positions, if you will, and so they're all equivalent, right? Unlike the trigonal bipyramidal. So these are our 5 basic geometries. And these electron geometries will also be the molecular geometries if we only have bonds. But what if some of our electron groups are lone pairs? Well, now we have to change our thinking a little bit. We have to adjust if instead of having a bonding group there, we have a lone pair. So let's look at what that does. So again, the actual geometry might be slightly different than what the electron geometry is because of the presence of lone pairs. Now, the reason for that is lone pairs, because they are not tied to another atom at the other end of the bond, occupy a larger area of space. So if we think about a bonding pair as kind of occupying a tube, right? Where you have the two bonding atoms at each end, and the electrons are sort of isolated within this sort of tube between the two atoms. If you have a lone pair, right, there's nothing at the other side here, so these electrons have more room to spread out, get away from each other, right? They are both negatively charged, and so these lone pairs occupy a larger region of space, and therefore they repel more, right? So you get greater repulsion, so that's going to tend to change the bond angles a little bit, and we're going to give these types of geometries different names, because when it comes down to it, the molecular geometry is based on the atoms that are present. And so while the lone pairs will dictate those angles, the actual shapes are going to be based on the atoms that are there. So if we think about repulsions, right, the most repulsive would be between two lone pairs, then a lone pair bonding pair, that's what we're talking about, and then bonding pair, which is what we see in the idealized geometries with only bonds. Now, if we have 2 electron groups and 3 electron groups, then we don't really think too much about what we call derivative geometries, right? Or geometries that come with this. That really starts when we get to 4 electron groups. So let's think about this. We start out with an idealized tetrahedron. But what if one of those 4 is a lone pair, such as an NH3, right? Now, and this is where the Lewis structure comes in, right? Because the Lewis structure is going to tell us whether I have, right, 4 bonds, whether I have 3 bonds and a lone pair, 2 bonds and 2 lone pairs, etc. So if we have 3 bonds and 2 lone pairs, we have a molecular geometry of what's called trigonal pyramidal. So again, it's a trigonal base, okay, where the nitrogen, in this case, or the central atom, is the top of the pyramid, right? So we just essentially name it based on what this part looks like. So a trigonal pyramid, right, where the nitrogen is the top and the hydrogens, in this case, represent the 3 legs of our trigonal pyramid. Now, the lone pair, of course, will influence the angles. And so we see that the angles are shrunk from the idealized 109.5 to 107. Now, if we go a little further and we have 2 lone pairs of our 4, then we get to a shape called tetrahedral bent. Right? So tetrahedral bent geometry. Now again, if you think about, we're just naming it here, right? We call this shape bent. Now some books will call it angular. And we can see the 2 lone pairs here, right, are going to repel each other a lot, right? So the biggest repulsions are going to be between 2 lone pairs, and so these lone pairs want to get away from each other. And so both of those are again going to push the hydrogens closer together, in this case, and so the bond angles get depressed even more, and we get, in water at least, somewhere around 104.5 degrees. So you can see that the angles within the structure get smaller as we add more lone pairs. So we have 2 derivative molecular geometries from our tetrahedral base geometry. We have trigonal pyramid with 1 lone pair, and we have tetrahedral where you have 2 bonds and 2 lone pairs. Okay, so let's move on to 5 electron groups. So we can have the traditional trigonal bipyramidal when they're all bonds, but what if we start putting lone pairs in? Well, the lone pairs on the central atom with 5 electron groups will occupy, now and this becomes key, and we'll look at a picture here in a minute, will only occupy the equatorial positions. So they will only occupy where the bond angles are 120 degrees. So around that central trigonal plane area. So if we replace one of those, right? So in our structure we have a total of 4 bonds in one lone pair. We call that a seesaw shape. Now, there's other names for it, but we call it a seesaw in this book. If we have 2 lone pairs, so 2 of our equatorial positions have lone pairs, we have what's called a T-shaped geometry. And if we get all 3 equatorial positions are lone pairs, then we just have the 2 equatorials, and we call that a linear molecular geometry. Now, the angles, of course, will be affected here. The equatorial angles will become less than 120, and the bond angles between the axial and the equatorial, which are normally 90, will become less than 90. Right? The exception here is, of course, in linear, we will have a 180-degree bond angle. Right? So if we get to where we have 3 lone pairs in the equatorial, then we switch to the bond angles in a linear shape. Okay, so let's look at some pictures here. So let's start off with our basic trigonal bipyramidal, right? So the first thing is we have to determine that the lone pair is going to go in the equatorial, or is going to go in the equatorial positions, not the axial. Now the reason for that is if you put a lone pair here in the axial position, it has what we call 90-degree contacts or 90-degree repulsions from 3 different atoms. The 3 fluorines here are the 3 atoms in the equatorial plane. So 3 90-degree contacts. If you put it in the equatorial position, it only has 2 90-degree contacts, right? Between the equatorial and the 2 axial positions. So this one is favored, right? We don't see this one here. So again, if I take one lone pair here, replace it, I name it based on the 4 atoms that are present, and you can see it kind of looks like if you rotate it so that the 2 fluorines here are our base, we get the ends of a seesaw, right? So these would be the 2 seats here, you know, here and here, and it would be like a seesaw if you were to flip it over. So that's where the name comes from. And you can see, you know, an example here, sulfur tetrafluoride. Now, if you have 2 lone pairs, you get what's called a T-shape, right? You can see if you name it based on the angles here, and you flip it around a little bit, it looks like a T. Right? And again, these angles are going to be, you know, less than 90 here. And finally, if all 3 of them are lone pairs, we get a nice symmetry here, and the 2 equatorial axial positions get as far away as they can, and you end up with a linear shape. So 3 derivative geometries that come from our 5 electron trigonal bipyramidal. Okay, and finally, what if we have 6 electron groups? Well, maybe surprisingly, there's only 2 geometries that we can get out of this with lone pairs. If you have 1 lone pair, we get what's called a square pyramid. And the bond angles are going to be less than 90. If you have 2 lone pairs, the second lone pair is always going to go 180 degrees from the first lone pair. So they're going to go on opposite sides of our octahedral, and that's going to result in what's called a square planar geometry. And the bond angles will be 90 degrees in that square plane. So let's look at pictures. So first you can see here, if we pull off one of our octahedrals here and replace it with a lone pair, we get what looks like a square-based pyramid, And so this is called square pyramidal. Right? And these angles are actually less than 90. So this is kind of like a weeble wobble, right? Where this bromine would be sticking down a little bit lower and the fluorines would be kind of sticking up off the floor. So it would kind of wobble there. But we call it a square pyramid. A second lone pair is only going to go in one place, right? It's going to go opposite this, right? They're not going to go right next to each other. They're going to go opposite each other, or 180 degrees apart. And so that sort of balances out this structure, and you end up with a square plane, which looks like this, where all of these angles now are 90 degrees. So the fluorines are at the corners of a square. So we have just the two. If we try to put any more there, the lone pairs get too close together and we no longer can do anything. So let's summarize how we pick this up. We're going to start off by drawing the Lewis structure. We're going to determine the number of electron groups around the central atom. That's going to determine what our base geometry is. Right? From there, we're going to decide if they have bonds or lone pairs. So if they're all bonds, then the molecular geometry is going to be the same as our base geometry. If we have any lone pairs, well, then that's going to lead us to one of the what we call derivative molecular geometries that stem from there. And based on this information, right, we're going to determine what the molecular geometry is and the bond angles. Now, there's a nice table in your book that lists all of this out with the electron geometries, the molecular geometries, and what the angles are. Now, I will tell you right up front, you will need to know those, right? That table will not be provided on an exam. You are expected to know those. And so, want to make sure that you start early to look at these. Okay, so we're going to end there. And next time, we'll talk a little bit about some other structures and get into how we determine the polarity of a molecule.